Greetings, nMigen friends. Today, for part 2, we're going to be talking about nMigen and actually creating just some small piece of hardware using nMigen so that we can get used to it and get used to the concepts. And we're actually going to install onto a physical board, namely this lattice evaluation board that I showed last time. So let's get started. So the first thing that I suggest you do is definitely look in the description and take a look at the nMigen tutorial that I wrote. Again, it's more a series of comprehensive notes to myself, but that will definitely teach you the basic concepts and sort of get you oriented around what nMigen is and what are the various concepts and things that it uses. So this code right here is what I consider to be the very bare minimum of a Python file that you're going to use with nMigen. So the basic concept is that of the elaboratable, which you can sort of consider to be roughly equivalent to a module. They usually have a one-to-one correspondence. However, that's not always true. So remember that in HDL terminology, elaborate means to take your code and replace all of the definitions and generate all the things that you need to generate to come out with something that can actually be compiled into hardware. And that's all elaboratable means right here. It means that it has an elaborate method. Now, the platform you don't have to worry about at this point. Platform actually means what hardware platform or evaluation board or regular board and chip you're going to be using. Platforms contain resources, mainly pins and clocks and things like that. So if you are interested in actually connecting up your nMigen hardware to the actual pins of the FPGA, that's where platform becomes important. But we're not going to do that right now. We're just going to look into simulating and formally verifying our module. So elaborate outputs a module. This is a Python type annotation. I strongly recommend that you use type annotations because otherwise you really have no information about what type a certain argument is or what the thing returns other than comments. They're just free form, right? So Python has a type hinting system which can actually check the types that you pass in and that are returned. So elaborate typically starts with creating just a module, which is an nMigen class, and returning that module. Now, this is something that I like to put into elaboratables. These are ports, and ports will basically return a list of what I consider to be public signals. And if you look down here in main, you can see that for main runner, I'm passing it ports, which basically means that these are the things that are going to be visible in traces. They're also going to be visible to formal verification. So that's why I just like to put that in. Okay, in your main, you're actually going to start up a parser and you're going to parse the arguments. And the reason that we do that instead of using the ordinary Python argument parser is that nMigen sort of is taking over that level. So you can actually do things like add arguments, but right here we're not going to do that. So the next thing that you do is you define a top-level module and you add your submodules to it. So here, the module that I want to instantiate is called adder. So I'm going to create an instantiation of adder, and I'm going to just call it adder. And I'm also going to add it to the submodules. This is actually a dictionary. I think it's a dictionary. But you can just say m.submodules plus equals adder, and that will sort of give you a module with no name. But usually it's very convenient to give it a name. So You can just say m.submodules dot the name of the thing that you're instantiating. So in any case, and then you run the main runner, which takes a parser, the arguments. So that's how you get your arguments into the parser, the top level module, and then the ports that you're interested in outputting to a trace if you're doing simulation, or making available to Yosis if you're doing formal verification. Okay, so that's the bare skeleton. So the next thing that I've done is I've defined our sort of public-facing signals, and you can see that I have an X, a Y, and an out. Notice that I don't actually specify the direction of the signals because the direction is determined by nMigen, by how you use those signals. You don't actually have to explicitly say what they are. So X is just an 8-bit signal. It's just 8 wires. You can also say whether they're signed or unsigned by doing something like unsigned of 8 or signed of 8. The default is unsigned. So we're just going to have 2 inputs that I'll call X and Y, and we have an output that I'll call out. So as you can guess by the name of this module, this is just going to add the two together. So let's do that by defining that logic in Elaborate. And that's all there is to it. So first of all, you can see, let's get this out of the way. I've added my signals to the ports, so now those are available for simulation or verification. This is basically the line that adds X and Y and outputs the result to out. Now, it doesn't look like ordinary Python where you would just say self.out equals self.x plus self.y. Remember that nMigen generates the hardware code for you. It doesn't actually translate Python to hardware. So what you're doing here is you're basically saying, okay, in the combinatorial domain, and again, check out the tutorial to understand what domains are. In the combinatorial domain, I have a statement, and that statement is that self.out is equal to x plus y. Okay, so let's see how we can simulate this. So the first thing that I did was I added these two imports, simulator and delay. And in main, first of all, I've commented out the main runner because that's really only useful for outputting code that you're going to run through Yosis. And this is not going to be run through Yosis. It's going to be run through nMigen's native simulator. So the simulator does have a bug associated with it in that it will not actually output the traces for input signals. So this is just a workaround. What I've done is I've declared just two local signals, X and Y, and I've added some combinatorial logic to just copy X into adder.x and Y into adder.y. So that's what these two lines do. And then I create the simulator based on M, which is our module. And it's very important to put these workaround lines before the simulator construction because constructing the simulator causes it to look at M and all of the signals that it has. So now it has an X and a Y signal. So the next thing that we can do is define a process, and a process is basically just something that the simulator will iterate over. It acts as a generator, so it's got yields. And what this does is the simulator simply looks at the process and generates one statement, and in this case the statement is x equals 0. Then it goes on to the next one, and the next one, and so on. And this is useful for when you don't have a clock. We'll get to when you do have a clock later, how to simulate that. But without a clock, we basically have to specify a delay, and this is a delay in seconds. So So what this says is set X to 0, set Y to 0, and then delay for 1 microsecond. And then we can look at the output. Then set X to FF and Y to FF and delay another microsecond. Then set X back to 0 and delay another microsecond. So we add that process to the simulator. There's another function called add sync process, which is for adding processes that use clocks. But again, we're not using a clock here, so we just use add process. And then we call the simulator's write VCD function. VCD is the output format or input format used by GTK Wave, which is a very useful waveform displayer. There's also a file called test.gtkw, and what that actually does is it's sort of like a configuration file for GTK Wave to tell what signals in what file you're interested in, so that you can just run your simulation and then load up the GTKW file, and it'll immediately pop up with all the traces you were interested in, as opposed to a blank screen and then you have to select the traces. So unfortunately, under the Windows subsystem for Linux, because it's running as a Linux program, the file that gets generated by write VCD, the GTKW file, refers to the VCD file as a Linux path. And unfortunately, if you're running gtkwave.exe, which is a Windows program, well, Windows doesn't understand that path. So it's just going to say, I don't know what that file is. So this is of less utility if you're using the Windows subsystem for Linux. You can, of course, run GTK Wave in Linux, or rather in WSL, but then you have to run an X server on Windows, and that just gets to be a pain. So anyway, and then you simply run the simulator and it will output the files for you. So let's take a look at that. So I'm just going to run Python 3 on adder.py, and now it's done. I mean, there was very little to do anyway. And now I'm going to run GTK Wave on test.vcd. And when we open it, we will see that, first of all, we need to select the top module, and then add X and Y to the traces. Inside the top module is adder. Remember I said that adding the module to the submodules dictionary using a specific name is very useful. And this is why, because the name pops up here. So we're going to add out. All right, now this is in picoseconds, and of course we're looking on the order of microseconds, so we need to zoom out. Okay, and there we go. 0 plus 0 is 0. FF plus FF is FE, and 0 plus FF is FF. So that is how we simulate it. Now, if you want, you can add some assert statements in here to make sure that the results are as you expected, which is great for just, doing a few tests, but really you want to do formal verification. So maybe we should do that. Now, as I think I've said in a previous video, formal verification is sort of like unit testing squared. In unit testing, you come up with some test cases and then you run your code through those test cases and make sure that the output is as you expect it to be. Now, what formal verification does is it says, okay, for your code, the following properties have to be true all the time, or they may be true in certain cases. And then what the formal verification engine will try to do is falsify that assertion. So let's take a look at how we can do a little bit of formal verification on our code. So what I've done here is I've added one more assert from asserts called assert. What I've also done is I've put back our main runner. I've commented out all the simulation stuff, and I've added a single assertion. Now, in this case, addition is fairly simple. What this proves is that I can actually copy code. That's really all that it will formally assert. However, this is a lot more useful when, for example, you would implement addition not using the plus operator and relying on nMigen and Yosis to do the right thing, but when you're actually, maybe you're constructing a ripple adder, or maybe you're constructing an adder out of smaller adders, and you want to make sure that you're doing carries properly and that sort of thing. In this particular case, all I'm doing is using, plus and plus right down here in the assertion. Let's take a look also at the SBY file, which is the symbiosis file. You can see that I have two tasks called cover and BMC. BMC is bounded, so you give it a depth, which is the number of cycles that the formal verification engine will run before saying, okay, everything seems pretty good. There's another mode called prove, which basically uses induction in order to prove that if everything works for n-1 steps and it works for n, then by definition it will work for all time. And we're not going to do that right now. All we're doing is bounded model checking. Cover is for when you want to make sure that a particular case can actually happen. So we'll look at that in a moment. Depth we set to 2. We could actually set it to anything, but 2 is just fine because we don't have any clocks. Multi-clock I turned off because, well, we don't have any clocks, and we certainly don't have more than one. The engine that I'm selecting is Boolector, which I found to be a pretty good overall proof engine. The script will read ilang, which is the intermediate language that is used by Yosis, and nMigen can output ilang. And basically, nMigen always generates a module called top, so that's basically how it works. So let's see what happens when we try to do some formal verification. So the first thing that we do is we run the Python program in generation mode. So instead of just python3 adder.py, the main runner looks at certain arguments. So it looks at the first argument and sees if it's generate or not, and then it looks at the -t option, which is the type of output that it's going to do. IL is for ilang and V is for Verilog, but when you're working with Yosis, you may as well just go straight to the intermediate language because, I mean, why would you have Verilog code? Unless I suppose you were giving the Verilog code to some other non-open source tool. So anyway, we're going to output this to a file called toplevel.il. So there we go, no errors. And we can actually look at the IL. It's understandable, but basically it's a bunch of cells that get connected to each other. And now in order to run formal verification, I run the SBY tool on adder.sby. Now if I run it, okay, that's great. So I see here done with pass, and this is for the cover mode, I believe. Where does it say cover? I'm sure it says it's somewhere over here, but I'm just not seeing it. The next mode that it does is BMC, and we can see down below here that it failed, which is really weird. Why would it fail? So we've got a counterexample trace over here, which we can look at using GTK Wave. So let's do that. Okay, so what we want to do is we want to look at the signals. So there's X, there's Y, and there's out. And we can zoom out to the very end, and we can see, well, okay, 7E plus FE is definitely 7C. So what went wrong? Well, in actual fact, 7E plus FE is actually 17C. So this is one of the traps that nMigen can lay for you, is that when nMigen sees an 8-bit signal added to an 8-bit signal, it generates a 9-bit signal. And then if you compare the 8-bit signal to the 9-bit signal, well, it's going to say, of course they're not the same, especially if the 9th bit is set. So the fix for that is to truncate to 8 bits. So this only happens when you're doing formal verification, because usually what you're doing is you're assigning the result of an operation on signals to another signal. And that, by its definition, will truncate the signal to whatever the destination is. Here, however, what we're doing is equality. So both sides have to be equal. And a 9-bit signal is just not equal to an 8-bit signal if the 9th bit is set. So let's go ahead and recompile and rerun. And there we see that we have passed formal verification. So I can be sure that no matter what inputs are given to X and Y, the output will be correct. Now, again, this isn't much of a test because I'm testing whether I can type plus in my module and whether I can type plus in my formal verification. But again, if you were implementing addition using some other mechanism other than just plus, then this verification is actually extremely useful. All right, we've talked about assertions. Let's talk about cover. Let's cover. So what cover does for you is it allows you to ask Yosys to come up with a sequence of inputs that generates the condition that you're trying to cover. So for example, I can add a cover statement that says, give me a set of inputs such that the output is equal to FF. And that's really all I need to do. Now for here, Yosys is free to choose anything it wants for X and Y. It'll probably choose one is 0 and the other one is FF because that's probably the easiest way that it can figure out to get to that number. So that's not that difficult. I'm going to add another cover statement, and it will search for both, where adder.out is FF and I think I need to surround these with parens. I can't use Python and I can't use Boolean and, that's the double, well, yeah, I can't use the Boolean and, which is that. In hardware, what you're actually doing is you're using an equality which results in a single bit, which is either 1 or 0. So that's why you have to use the bitwise and then you have to surround your terms with parentheses because I think the bitwise and takes a higher precedence. So it might do, address.out equals and then internally parentheses FF and whatever, which is not what you want. So what I'm going to do is I'm just going to add another condition where adder.x is equal to FE. So of course it should find adder.y being 1. So this is not that interesting for purely combinatorial circuits, but for things like clocked circuits, where you really need a sequence of input signals, this is much more interesting and much more useful. So these are the two statements that I've added. Let's go to the SBY file. So we're not going to change anything because we already have our cover task set up and we don't have any clocks, so a depth of 2 is just fine. So now let's go ahead and compile. So the first thing that we do is compile. Okay, I forgot to add an import for cover, so let's do that right now. It's in nMigen asserts. Cover. Try again. Great. And now we'll run SBY. Okay, and the bottom part is for bounded model checking, which we know passes. The top part is for coverage. And what we're looking for is a log message that says reached cover statement at adder.py35 and reached cover statement at adder.py36. So this tells you that it found a way to make those statements true. Now the interesting thing is, well, let me go ahead and do this. I'm going to change this so that adder.out is equal to 0 and adder.x is FE. because I want to emphasize the fact that the cover statements don't have to interact with each other. So I can choose different cover statements that may actually contradict each other, and Yosis will find cases for each one. So let me go ahead and recompile and run SBY again. And we can see that we found, again, one cover statement and another cover statement. And it also says that there are some traces that I can look at. So let's go look at those traces. We'll look at the first trace, which corresponds to line 35. And line 35 is just checking that the output is FF. So I run GTK wave on, I think it's cover something cover. Unfortunately, it doesn't tell me the full path, not like BMC does, which is kind of a pain. So I think it's test something. No, what is it? Adder cover. Engine 0. Trace 0. And let's see what it came up with. So if I open up X and Y and out, you can see that X is FF and Y is 0, 0. So Yosis basically says, these are the inputs that will give you what you want. Let's take a look at the other trace, which is trace 1. This is where we set the output to 0 and one of the inputs to FE. So if we look at that, we can see that the one output is FE, the one input is FE, the other input is 2, and the output is 0. So again, Yosis has figured out exactly what inputs need to change to in order to get the result that you want. Now, if you put in a cover statement that absolutely could not be met, like for example, and adder.y equals 0, then Yosis will spit out an error saying that it could not meet the cover statement within the specified number of cycles, which in this case would be 2, but of course, we know that it's never going to happen. So that's cover. Okay, so I've added an assumption here, and the assumption basically says that x has to be equal to y shifted left by 1. So in other words, x is twice y, modulo 256, of course. So what this assumption says is we're restricting our inputs to these particular values. And you have to be a little careful when you're using assumptions and BMC, which is the asserts, because what those assumptions do is they restrict your inputs to certain values. And then when you do your asserts, you're basically saying that no, the inputs can't be any particular value, they have to be these particular values, or they have to satisfy these assumptions. Which is useful if you know that your inputs have certain illegal states. They don't have to be inputs even, they can be internal, flip-flops for example. So you can basically say, well, these are the illegal states, so I want to assume that you're not in an illegal state. So what we're going to do is we're going to put together a little more complex cover statement right over here. We're just going to say that the output has to be greater than 0 and less than 40. So the question is, can Yosis find an input x and an input y such that y is twice times x? So let's go ahead and compile and run, and we can see that indeed Yosis has found something. So let's take a look at the trace and see what it found. All right, so it found 6 and 3 is 9. So that makes perfect sense because I just specified that out had to be between 0 and 40, not inclusive. And Yosis just found 6 and 3, which satisfies x is twice y. I think I misspoke before. But yes, x has to be twice y. And the sum has to be between 0 and 40. So there you go. Anyway, that is a quick look at how you use asserts, assumes, and covers. Now you can add other interesting things, like, for example, let's suppose you wanted to cover something, but only in another circumstance. So, for example, we could do this. With m.if, let's say adder.x is equal to adder.y shifted over by 1. Then cover this statement. So in other words, this cover is only active when this statement is true. So this is another nMigen construct if it looks like a Python context. This will probably end up being equivalent to the assumption. However, the interesting thing is that because I didn't use an assume, it means that when I run BMC, it will run over the full input set to make sure that the assert is always true. Here what I'm saying is I'm asking Yosis to cover only if this statement is true. I could stick the assert down here under the if, and then it'll have the same effect as an assert. So let's run this and see what Yosis comes up with. Okay, it has passed, and let us look at the trace. And the trace shows... Interesting. Okay, this time it chose BE and 5F to be 1D. Effectively, when you're asking Yosis to do covers, it will sort of try to get the simplest result, but in some cases it's just going to be random. It's just going to be, you know, well, you asked for this, and this satisfies those conditions. In general, when you're dealing with clocked logic, Yosis will try to find the lowest number of clock transitions that lead to your conditions for coverage. So that's pretty much that. Speaking about clocks, let's look at clock domains. Every module in nMigen gets a clock domain called sync. Cync. I have this module that I've called clocky because it's a clock. So what I've done, you can see that I have a 7-bit signal just called X, and a load signal that's 1 bit, and a value signal that's 7 bits. And the idea is that X is going to count up on every positive edge of sync, and you can also set load high and put a value in value, and that will load the value into X on the next clock pulse instead of incrementing by 1. So here's the logic. So we can see with m.if, so if self.load is true, then on the next positive edge of the clock, then self.x equals. Now mux is basically like the ternary, you know, question mark colon that you see in C, Java, that sort of thing. So what mux is basically it uses a 1-bit signal as a condition, and then if that bit is true, then the value of mux is the first value, otherwise it's the second value. So basically what this is saying is on the next positive edge of the clock pulse, set x equal to, if self.value is less than or equal to 100, then the value that you want to load in, otherwise just 100. So here I'm basically limiting the value that you can put in to 100, just for fun. Elif, so this is the equivalent to Python elif, so else if self.x is 100, then on the next clock pulse, or the next clock edge, put 0 into x, otherwise increment x, so set x equal to x plus 1. So that's really all this thing does. So basically it's a counter. It counts up to 100 and then it resets. And you can also load it with some value. And if you try to put in a value that's greater than 100, then it will go ahead and limit it to 100. So that's all this thing does. So here I've added X, load, and value to the ports that I want to give to any external process like Yosis. And here is the main. As before, we have our standard workaround where input signals are not actually output to the trace file by nMigen unless they are in the top level module. So here is where I'm putting it in the top level module. Here's our simulator instantiation that we've seen before. What's different is we now add a clock, and you can specify the clock period in seconds. So this is 1 microsecond. So the idea is that the clock has a 1 microsecond period, or it's 1 megahertz. Okay, let's skip process for the moment, and at the bottom we can see sim.addSync process instead of just add process. So this is what I mentioned before, is when you have a clocked process, you add it using addSync process and not add process, which would be for combinatorial processes. Okay, so if we look at process, it looks a little bit different. Yield, just by itself, will cause 1 clock cycle to go by. Yield with some statement in it will cause that statement to be executed right away. So basically what this is saying is wait for 1 clock period, then set load equal to 1 and value equal to 95, and then wait 1 clock period. Then set load to 0 and wait 1 clock period, and then wait a bunch of other clock periods. That's really all that does. Everything else is the same. So let's go ahead and run this. Okay, so it has simulated, and let us open up GTK Wave to look. And at the top we have load and value, and inside clocky we have the clock and the reset. Now, of course, it doesn't look like it's doing anything, but that's because we're still in the picosecond range. So let me just increase the zoom. Okay, that's probably fine. All right, so here's X. Let me go back to top and get load and value. All right, so we can see that there is actually 1 clock edge before the process actually starts. So because signals by default get reset with zeros, so X is 0. So on the positive edge, we get 1. So the next thing that happens is I ask for load to get set to 1 and value to get set to 5F. The unfortunate thing is that just by looking at this, you can't really tell whether that happened just before the clock edge or just after the clock edge. In actual fact, it happens just after the clock edge. So this is the yield. Then we set load to 1 and 5F into value. Then another clock period goes by, and during that clock period, load is 1 and value is 5F, which means that 5F gets loaded into our counter. And then we do a bunch of yields, just to show that we're incrementing. And in fact, we're incrementing to 6, 4, which is 100, and then back down to 0, and then we continue 1, 2, and 3, and so on. And that's really all there is to it. So again, it's a little bit confusing when these signal changes, because if you zoom all the way in, these signals change basically right on the clock edge. So you have to sort of remember that signals, these input signals actually change just after the clock edge. Okay, let's look at some formal verification using a clock domain. It again may seem pretty simple and straightforward. Our logic isn't really that complicated, so there's not a whole lot to verify, but let's go through the exercise anyway. So I've commented out the simulator stuff and added back our main runner, and I have an assert. So in this particular assert, I want to make sure that if the value of the clock is greater than 0, then, now what I want to write is, then the value of the clock is equal to the previous value of the clock plus 1. So, in other words, the clock incremented. Obviously, I don't want to handle the case where x is currently 0, because then I would have to say, oh, well, then the previous value should be 100. And in fact, I could add that in later. So this is the property that I want to assert holds if, and only if, the output is greater than 0, that clocky.x is equal to the past value of clocky, that is, the value of clocky.x 1 clock cycle earlier, plus 1. And then, of course, I use the usual trick of truncating the value so that we're not comparing, 8-bit values, 7-bit values to 8-bit values, that sort of thing. So let's run this and see what we can come up with. Okay, so I generated the code, and now I am just going to run clocky.sby, which looks exactly the same as adder.sby, with the exception that I've set the depth to 40, because I just want to make sure that the thing works for 40 cycles. Okay, let's run it. Oh, and look, we've got a failure. So let's see why. Well, if I pull up the trace for BMC, and I look at the clock, and I look at reset, okay, the clock is going, reset is low, X is 0, but then it went to 40, and then 41. That's pretty weird. What happened? Well, it looks like what happened is that formal verification found a case where the value of X was 40, but it was not equal to the past value of X plus 1. And the reason is that it said, oh, I can just load a value into X, and I have just violated your assertion. And again, it will try to find the shortest path to that falsification of the assertion. So we can see that, it's also set value to some, random other values. That doesn't matter. The point is that we can look at this trace and we can see, oh, those are the inputs that falsify my assertion. So now I know that I have to be careful about the load signal. So let's go ahead and include something about load. So I want load to be 0. But not only that, I also want the past value of load to be 0 as well, because if the past value of load is 1, then we're just loading X, and then we can't have our assertion. So what I want to do is I want to say, and I guess I could just say past of clocky.load is equal to 0. I guess the present value of clocky.load doesn't really matter, because the present value of load will only affect the future value of X. So let's run this and see what happens. Okay, and we can see that it ran through to the very end. Great. Okay, I've added one more assertion that I want to check. I want to make sure that the clock rolls over properly at 100. So basically, if X is 0, then the past of X must have been 100. Now, this is not necessarily going to be true, right? Because at the beginning of time, it's probably going to start with 0, but let's see what happens. Okay, and we did get a failure. So let's see what verification came up with. Okay, there's our clock. There's our reset. Oh, it looks like we're resetting something. Our load, we're not loading anything. And we've got X. Aha. So the present value of X is 0 over here, but the previous value of X, or the past of X, is also 0. Why? Because Yosis decided that, well, we can always reset the clock. So if the clock was 0 and we reset it and it's now 0, well, you didn't roll over. Obviously, we need to take that into account. So what I've done here is I've just added another clause basically saying that the past of reset has to be 0. The tilde is negation, so basically I'm saying that that we want the negation of past reset to be true. In other words, reset needs to be 0 in the past. Oh, okay, name reset is not defined. So I need to tell what reset is, and the way you can get the reset signal for a clock domain is by just saying reset signal, and then you can name the clock domain here, but by default it's just sync. You can do a similar thing with clock by saying clock signal, but we don't actually need that. So that's my reset signal. Okay, let us run. Okay, we've got another failure. Let's see what that is. Clock, reset. Okay, reset is 0. X is 0, and then it goes to 0, and then it goes to 1. What happened? Load was set. Okay, that pesky little load. So what you can see is that we have to be really careful about the conditions that we want to check. So let's also say that we want not past clocky.load, which is basically the same as past clocky.load equals 0. And now we've passed everything. Okay, so what we can do now is we can probably just test load. So with m.if, if in the past clocky.load was true, then in the present, we want to assert that clocky.x is equal to, also from the past, the value that we wanted to load in. Okay, now what landmines can we think of? Well, what happens if both reset and load are set? Well, so it actually turns out that reset takes precedence over basically everything. So what's going to happen is we can have reset and load go off at the same time, and we won't actually load anything. Right? Let's just prove that by running this as is. And as expected, we have a failure. And if we pull up the trace, we can definitely see that reset is high and load is high. So of course, that's not going to work. So let's go ahead and fix that by also stating that reset must not be high. Okay, we've got a failure. Why do we have a failure? This is probably going to be interesting. So reset is low. We've got our load. Ah, okay. All right, so we've got some interesting things happening here. Notice that when the past of load was true and the past of value was 7,1, the current value of the clock is 6,4. Why? Because we cut the value off at 100, so we're going to have to take that into account. So let's see, what should we do? I guess what we can do is we can put in an assumption. Why not? So we can say m.d.combinatorial assume that clocky.value. Well, we don't really want to assume because I guess at some point we might want to test what happens when clocky.value is greater than 100. So, well, why not do this? Why not put in a multiplex, right? If the past of clocky.value is less than or equal to 100, then past of clocky.value else 100. And again, we're getting dangerously close to the territory where all we're proving is that I can type the same thing again, because this is exactly the same logic. So you might want to break this up into two statements. Basically, the idea is that if you write code in one way, then you want to prove that the code works in a different way. But let's just continue. Okay, we've got pass. Okay, so I think that's really all I want to do about this. Let's briefly talk about cover. So let's just say m.d dot, would it be combinatorial or sync? Let's try sync. Plus equals cover. Now I want to cover the case where clocky.x is equal to 3. All right, so I want to see what sequence of inputs cause 3 to be output, and typically it's going to be the shortest possible trace. So let's just run this. Okay, so let me just go up, and we do have a pass for our cover statement, so we can look at trace 0 and see what Yosis determined was the way to get to an output of 3. So there's our clock, there's our reset. Here's our load, here's x, and here's our value. So what Yosis decided is I'm going to load 3. Okay, that's perfectly valid. What happens if we want to say, but we don't want you to load? So what I could do is I could just say with m.if, past clocky.load, not that, then cover that case. So in other words, don't use load to load into 3. And what do we have? Clock, reset, load, x, value. Right. It just loaded 2 in and then clocked it once, and then we've got 3. So obviously we can do this exercise with restricting load. And then Yosis will be forced to start from 0, clock to 1, clock to 2, and clock to 3. Now the interesting thing is that, what happens if you try to cover the case where the output is 99? Well, the problem is that you will not be able to find a sequence that does that because you have restricted, according to the SBY file, your depth to 40. So you would have to increase your depth to something like 100 in order to actually cover that case. So you need enough runway, basically, to find your signals. Okay, so that's formal verification with a clock domain. So we've got one last subject to cover, I promise, and then this video will be over. And then we'll get to part 3, which is actually working on the CPU. But the subject is, how do we get the stuff that we wrote in nMigen into actual hardware? Okay, so here is the Lattice evaluation board, the ICE40 HX 8K breakout board. It's got a bunch of 1 populated connectors, 3 unpopulated connectors. It's got a bunch of LEDs on it. This is the Lattice chip itself, and down here is the FTDI USB interface. So it also comes with a cable. So when you just plug it in, it comes preloaded with just a blinky. You can see that it is blinking. It's got a power LED on the bottom. It's got 8 LEDs on the top. There's also another LED, which I'm not quite sure what it does, but it's labeled D1. And the ones on the top are labeled D2 through D9. So this is what happens when you just first power it up. So that doesn't mean you can program it or anything. So in order to program it, we are going to need to load some software, which is unfortunate, but that's what you have to do. So first things first, this is the FPGA Wars GitHub repository. FPGA Wars, I don't know why it's a war, but okay. And the first thing is that we have to load the FTDI driver. This is a more open FTDI driver than the ordinary FTDI driver. And it allows other software to communicate with FTDI chips. So there's this find all program which you can just download and unzip and open it. And here we see findall.exe. This is a Windows program, so you can put it in any Windows location. It should all be accessible through WSL. Now, if I just run, where did I put it? On my F drive. So if we just run it, it'll say number of FTDI devices found 0 because I have no FTDI devices plugged into USB. Now, if I plug in the Lattice board, okay, so it's blinking. And then if I run this again, it's going to say that it found one FTDI device, but it can't really communicate with it. And that's because we don't have the correct open driver installed. So that's what we're going to do. Let's see. The driver that you want to install is called libusbk. So first we want to make sure that we can actually see the device. So I'm going to plug it in again. Now for Linux, I think this is as easy as going into the USB or the device configurations and setting it up properly. It's just one file. But for Windows, it's a little more involved because unfortunately the Windows subsystem for Linux does not yet support USB, or if it does, it only supports certain devices. Definitely not this one. So the first thing that you want to do is pull open the device manager. There's the device manager, and you want to look under USB, and you're going to see USB serial converter A and USB serial converter B. If I unplug the thing, those two devices go away. Plug it back in. Okay, those two devices reappear. There's also this USB composite device, which also appears. So the thing is that the serial converter does nothing for us. It is not capable of communicating, or rather the program that we're going to use is not capable of communicating with that sort of thing. So the other thing that the instructions show is in devices and printers, you should see the new device, Lattice FT USB interface cable, and that just says that that your Lattice board is connected. So we can pull open devices and printers, or rather printers and scanners. This instruction manual was written for Windows 7, so it's different on Windows 10. You go to Bluetooth and other devices, and you can see down here the Lattice FT USB interface cable is there. But there are no options except to remove the device, which is obviously no good. And what they're talking about is this thing which has these, large friendly icons. So where do we find that? We find that under devices and printers. So all control panel items, and you go to devices and printers. And there it is right over here, Lattice FT USB interface cable. Now if you double click that and you click on hardware, you can see USB composite device, serial converter A, serial converter B, and it happened to load it on COM6 as basically an emulated serial port. So that's what we need to change. So you can see here, they have the same thing. Okay, so Zadig is a Windows application that will install the nice USB driver. So we can go there. You can download the executable from this link. That link goes to Zadig 2.2. Let's just see if there is anything more recent than 2.2. There is. It's Zadig 2.4. Sure, let's download that. We can, I guess, run it. Okay. Let's go back to the instructions. Okay, execute Zadig. Great. Initially, no devices are listed. select the option menu and click on the list all devices. So options, list all devices, okay. Done that. In this example, 11 devices have been found. Well, there's an awful lot of devices here. So now click on the driver bar and select the lattice interface cable for interface 0. Let's see, lattice, here it is. Okay. Okay, and basically we can see that the current driver is just FTDI bus, which is the unfriendly version, and we are going to change it to libUSBK. Excellent. Okay, and it shows here the USB ID. So this is basically the equivalent of USB devices on Linux, where Windows will look at the USB device that gets connected. It will look at the USB ID, the vendor ID, the product ID. In this case, it's 0403 and 6010. I think the 00 is the interface number, but in any case, once that comes up, Windows or even Linux will look into its internal database of device drivers and will say, oh, okay, I need to load this device driver for that device. So what we're doing here is we're saying when you find a USB device that has 0403 as a vendor and 6010 as a product, that is the lattice evaluation board, then load the driver libUSBK. Okay, so we're going to click on replace driver, which for some reason takes a long time. I don't know why. Oh, okay. Installation can take some time. Thanks for letting me know. That is actually nice UI practice over there. Okay, the driver was installed successfully. Close. Now you can see that Zadig is reporting that the current driver for this device is libUSBK, and that's pretty good. So I believe we can now close this. I am just going to unplug the board and plug it back in. Great. And now let us look at the device manager under USB, and we can see that USB serial converter A has disappeared, and that is correct. And if we look, there is a libUSBK device, which is the lattice FTUSB interface cable, which is correct. Okay. Oh, and it says if find all does not work after installing to interface 0, try to install to interface 1 also. Okay. Please note, this could break things. Wonderful. So now the next thing that we're going to do is we are going to run find all again, and we can see that it is recognized. That is because find all is able to communicate with libUSBK, and libUSBK is able to communicate with the device. So that is really how you install the driver specifically for the board. Now, why did we do this? It's because we want to run a program called iceprog, which programs ICE40 devices like this, and the only way that it can do that programming is through the correct device driver. So if we go to this other repository for FPGA wars called toolchain-icestorm, and we go look at the releases, we can see that there are a bunch of releases that include statically linked binaries for Yosis, icestorm, and Arachne PNR. And the thing that we're really interested in is icestorm, because we have already installed Yosis and Arachne PNR, or actually Next PNR, on Windows Subsystem for Linux. So the only thing we're interested in is icestorm, which is the actual programming software. So what I'm going to do is select Windows x86 1.11.1. After downloading, we should get a bunch of files, actually one file in here. So it's a tar, it's an archive of a zip file, and if you go inside the zip file, you see a bin directory, and inside the bin directory, you actually see a whole bunch of utility programs. And the program that we're interested in is iceprog. So you can go ahead and extract that to any Windows drive. And I have it installed under F, so mntf iceprog. We can run it. Why don't we do this for Linux? Well, again, the Windows subsystem for Linux does not recognize USB devices. So we have to go through the Windows program. So it's basically saying missing argument, which is great. If we go to the help, we see that there are a bunch of things that we can do. The thing that we are really interested in is -b. And what -b does is it bulk erases the entire flash before writing. Typically, you want to do that. And then you can give it an input file, and that should actually load the program. So let's actually put together a program and generate a binary bit stream out of it and load it on the board. So what I'm going to do is I'm going to create a module called Blinker, and in it, first I'm going to access the platform's default clock frequency. You can always get this because platforms have a default clock frequency. So what I'm going to do is I'm going to set up a timer, and all cards on the table. I stole this mainly from the examples from nMigen. So that's why it looks like this. So we're going to define a timer signal. The maximum value for the timer signal is just going to be whatever that default clock frequency is divided by 2. Now the default clock frequency for the board that I'm using is 12 megahertz. So obviously if we want the timer to go off at 1 hertz intervals, we need to toggle it at 2 hertz, basically, which means that I need to count 6 million counts of the clock and then do a toggle. So 6 million is just basically the clock frequency divided by 2. So by using max in a signal, I can say what the width of that signal is. So for 12 megahertz, or rather for a maximum count of 600 million, that's about, I think, 23 bits. So nMigen will basically look at max and say, okay, how many bits do I need in order to have a maximum of this number? And the answer would be 23 bits. Reset here tells me that when the board powers up, or whenever you toggle the reset pin, what should the value of the counter be set to? And in this case, it's going to be a countdown counter. So we're going to start it from whatever the maximum we want, -1. So the next line here is basically the fun part. This is where you get to have signals associated with actual pins on the FPGA. So you can request a named resource, and this particular resource is called LED, and we'll get to that in a moment. The LED resource is an output pin, so I use .o to specify that I want the pin's output signal. So LED is now a signal. You can use .i for an input. If it's a tri-state pin, you can say whether the output is enabled or not by using OE. If it's a bidirectional pin where you have both .o and .i available, then .oe tells you whether you're doing inputs or outputs. So .oe, if it's 1, you're doing an output, and if it's 0, you're doing a read. All this information is in the tutorial. So the next thing is that if our timer reaches 0, then we want to go ahead and just set the timer back to its max value and toggle the LED. Otherwise, we just want to count down on the timer, and that's basically it for the Blinky program. Now, how do we get this mysterious platform? Okay, so the first thing you have to decide is what basic platform or base platform you're going to derive a board from. Now, there are a variety of base platforms, and I enumerate them in the tutorial. But if you look at the website, if you look at the GitHub repository under nMigen vendor, you will see the different devices or base platforms that you can use. So there's an Intel FPGA, there's the Lattice ECP5, the Lattice ICE40, and so on. And some of these are compatible with Yosis, some of them are not compatible with Yosis, and then you have to use the vendor's tools. The Lattice ICE40 I particularly like because it's supported by Yosis, which is nice. So it's all open source and it's pretty fast. So because I'm using an ICE40 device, if we look inside here, we can see that the name of the platform that I need to derive from is called Lattice ICE40 platform. Okay, and there's a lot of information in here about the required tools, how it works, what the output files are. If you use the IceStorm, which is the open source tool chain, this is what you have to do. If you use IceCube 2, which I think is Lattice's thing, either LSE or Simplify, I guess, this is what you have to do. So we're actually going to be using IceStorm. So anyway, that's the base platform. Now, if you don't want to bother with deriving all the board characteristics from a base platform, you can always go to the nMigen boards GitHub repository, and it has a list of predefined boards. So for example, I could have chosen the ICE40 HX8KB evaluation board. B, I guess that's breakout. And as you can see, it derives from Lattice ICE40 platform, and it defines all the things that you kind of want to define, so you can use it straight or you can use it as a starting point. So I used it as a starting point because I actually don't need a lot of what is defined, just for my simple example. So here's the simple example. I'm just going to call it board. Now what you have to do is you, specifically for the Lattice ICE40 platform, and different platforms are different, so be sure to look at the GitHub repository for the platform you're using. You need to specify the particular device that you're using. And again, if you look at the class in the GitHub repository, we can see a list of devices that you can specify. So of course, I'm going to be specifying the ICE40 LP8, the ICE40 HX8K, because that's what I'm using. And you can see that it translates to various toolchain options. Same thing with package. The particular package that comes on the breakout board is a CT256. That just means that it's a BGA with 256 pins on it. So the important part, the really important part, are the resources. So these are named resources, and they basically tell you what pins are what. So for example, on the board, there is a clock that is connected to pin J3. The reason that it's connected to pin J3 is that it is a global buffer. And here you have to look at the chip's data sheet. Global buffer basically means that if you input a signal into this pin, it's available all over the chip, or at least maybe all over most of the chip or a part of the chip or whatever. The point is that it's a signal that you can get a very high fan out. So you can feed it to, thousands and thousands of lookup tables and flip-flops and things. So obviously when you have a clock or any signal that is going to go to a whole bunch of flip-flops and lookup tables, you want it to be global. So in this particular case, I'm defining a resource called clock1. 0, I think, lets you specify if you have multiple pins. I'm not quite sure what this number does, but I'm just going to set it to 0 and we'll leave it at that. Pins, that tells you one or more pins that are associated with the resource. Now in this particular case, I don't have more than one pin associated with the resource. In the example for the board, we can see that there is a resource here where we're describing a whole bunch of pins for LEDs. And I don't really want to do that because I only have one LED. But anyway, so this allows you to specify which pin is associated with that resource and what the configuration for that pin should be. Now, the configuration for a pin is either going to be input, which is I, output, which is O, bidirectional, which is IO, or tri-state, which is OE. And this is gone over in the tutorial. Then for clocks, you want to say what the frequency of the clock is. So in this particular case, for this particular board, the clock that is connected to the chip is 12 megahertz. And then you want to specify the chip-specific attributes. And these attributes, first of all, they have to be supported by the platform in nMigen, so you need to know what they are. And second of all, they have to be supported by the tool chain. So global equals true. Again, this tells you whether it's a globally buffered pin. And IO standard tells you the voltage standard. Now, when you're using the vendor's tool, you can specify things like low voltage CMOS 3.3 or low voltage CMOS 2.5. And that basically configures that pin for the particular voltage standard that you're trying to apply to the pin. Not many modern FPGAs have a TTL standard. So they're all basically low voltage CMOS 3.3 volts and below. So the fact that this just says SB underscore LV CMOS, I don't exactly know what that means. I do know that it translates to 3.3 volts, low voltage CMOS. I don't know if there are any other IO standards for this chip supported. I've looked in the source code and I don't really see anything else. So if you know the answer to that, leave a comment, because that would be kind of great to document. All right, so that's clock one. We also need a reset for a clock. So again, it's a good thing to put it on a globally buffered pin. So in this particular case, it's pin R9. The direction is an input, and of course it's a global pin, and the IO standard is low voltage CMOS. And finally, I have the LED that I want to blink. The particular one that I want to blink is connected to pin C3. In order to determine the pins, you need to look at the documentation for the board. This is the one known as D2. It is an output pin, and it is not a global pin, and its IO standard is low voltage CMOS. Okay, so those are the three named resources that I really need for my hardware. If you want to define more resources, you can do that, and then you can name them. Things like buses, so for example, let's suppose you had a 16-bit address bus. Well, you could say resource address, and then there should be some way of specifying 16 pins. I know that the string here is space separated, so you can specify 16 pins one after another. Again, I'm not quite sure what this number means. Maybe because you can have LED 0, LED 1, LED 2, and so on. And I guess the default, when you request one of those pins, is resource number 0. Okay, all boards have to have a default clock. So this is what the sync domain is going to be connected to. You also need a default reset, which is, again, what the sync domain's reset is going to be connected to. And then you need to specify connectors. I have not figured out exactly what connectors do. I just know that you need a list of connectors. Again, if you look at the example board that is given by nMigen boards, all of the connectors are laid out, and it seems to be the jack, the number, and then the pin layout. Again, I don't know what purpose that serves, but I do know that if you leave connectors out, you get an error. So let's just leave it at that. Finally, there's this snippet, which I stole completely from the example board. This allows you to simply run the entire tool chain when you run the Python program, which is convenient. You just plug in your board, run your Python program, and it programs itself. I'm using, unfortunately, the Windows subsystem for Linux, and WSL does not support many USB devices, and it certainly doesn't support these FTDI USB devices, which means that I can't automatically run iceprog. In fact, I might actually be able to change this to iceprog.exe. In other words, I can't run the Linux version of iceprog because it's going to look for a Linux USB device driver. I have to run iceprog.exe, which is the Windows program. So I could probably modify this to look for iceprog.exe. This thing here, I could probably just replace with iceprog.exe. Interestingly, it calls it with minus capital S and not minus B. I don't know why, but in any case, the final piece of the puzzle here is what you call in main. So the first thing you do is you construct your board, and then you call its build function. The build function takes a module. So in this particular case, we're going to construct the blinker module and pass it to build. And then the key argument doProgram will tell the program whether to actually program the board or not automatically. So in this case, I'm setting it to false because I can't run the Linux version of iceprog. If you are on a native Linux platform, or if you're doing this from Windows, I assume that you could just say doProgram equals true and it'll just work. And that's pretty much it. So now let's run blinky.py, and that's it. The build files are put in a directory called build. And if we look at it, there's a whole bunch of files. They're interesting to look at. The file that's really the important one is top.bin. That is the bit stream that gets sent to the board directly. But you can look at the other files. One of the other important files is top.rpt. This is a report file, and it tells you exactly what the Yosis and iceprog toolchain or iStorm toolchain is doing in order to synthesize your file. So for example, you can see here that the input file name is top.il, and we know what IL files are. And really the interesting thing is way down at the bottom. This is a report of how big your implementation turned out to be. So we can see that we used 84 lookup tables and we used 149 cells. SB carry is the number of carry units, and this generally has to do with when you have adders. So of course, because we have a countdown timer, we implemented it basically as an adder, where you add -1 each time. So it used 27 of these units. Can you do better? Oh, absolutely, because of course, when you do a countdown timer, all you really care about is setting it to the initial value and then waiting until it counts down to 0. You could use something like a linear feedback shift register, and then you wouldn't have any carries. It would certainly be a lot faster. You wouldn't have any addition logic because you're not really doing addition. All you're doing is you're counting in a sort of kind of pseudo-random sequence. But the problem with linear feedback shift registers is that you really have to step through the shift register one by one in order to determine what the actual output is. So it doesn't go 0, 1, 2, 3, 4. It may go, 0, 15. Well, it doesn't go to 0. It may go, 1, 15, 4, 17, 95. Again, it's pseudo-random, and you can determine what the sequence is. But of course, if you want to implement something like a countdown timer, then you need to know what to set your shift register to in order to get the right value, when you clock it, however many times you're going to clock it. Okay, that's enough of that. The point is that you can run your program and look at the report, and then you can modify your program and then run this thing again and look at the report. There is a random component in how synthesis works. So it's a somewhat deterministic random process, which basically means that if you make a tiny change in your logic, it may actually change the way that that place and route actually works. So your blocks may be placed in different locations. Things will turn out differently. So when you make a change and you see the number of lookup tables go down, your logic may be more optimal if the number of lookup tables goes down and stays down. But often you'll just see it go up and down and up and down. And sometimes you'll make a change where it will go down and settle at that level. And then it'll maybe go up and down, at a lower level. So just be aware that when you make a change and you see your number of lookup tables go down, don't celebrate. Obviously, that is the true number of lookup tables that is used in the FPGA. It's just that if you make another tiny change that maybe you think shouldn't have any effect on the number of lookup tables, and then all of a sudden you see your number of lookup tables go up, it's not your fault. It's just, that's the pseudo-deterministic nature of place and route. Let's go ahead and attempt to, it was actually build, but I'll just do it anyway. Oh, wow, it actually recognized it. Great. So right now it's doing an erase. And looking at the board, you can't really see it. Let me see if I can dim the lights. There we go. So these LEDs at the top are just sort of lit. They're not blinking. It's dim. Okay, now it's reading and it's programming. And what do we see? Well, we see that one of the LEDs is blinking, which is exactly the program that we wrote. And it is blinking at a rate of 1 hertz, which is correct. Excellent. So we know that we can program this board properly, which was the whole point of this particular exercise. Now, the other interesting thing is that we can see that one of the LEDs is blinking, but if I bring it in a little close, you can see that the other LEDs are actually lit dimly. And I think that this is probably because we didn't actually set the level for those LEDs. So it's just sort of like, I don't know, floating there or something. So presumably we could change our program to actually zero out those LEDs, and hopefully that should make the LEDs go not lit, go off. Okay, now I've got the board unplugged, and just to show that we have actually put the program in Flash, so we don't have to reprogram it again, which would be kind of a pain, but let's go ahead and plug it in, and we can see that our LED flashes again. So basically what happened is the program on FPGAs is stored in Flash, and then every time the FPGA starts up, the program gets loaded from Flash into all of the FPGA lookup tables and flip-flops, and then it begins. So some of the older FPGAs have external flash. The newer ones, like this one, has internal flash. And that is why they're called field programmable, because they're, I guess, programmable out in the field, whatever that means. The field usually refers to some place where you don't have a development environment. So I guess if you can flash the memory, you can reprogram the FPGA in the field. So now the interesting thing is that now there's this other LED which is lit, like up here. Sorry, I'm looking at the video and I'm trying to move my hands in the right direction, but everything is upside down and backwards. But anyway, you can see that one of the LEDs is also strongly lit on. Again, we did not specify what the output of that LED should be, so effectively it's random. So if you have outputs, make sure that you set them to some known value, otherwise they'll just be random. Well, that's it for this video. It's been quite a long slog. This has been about an hour and a half, which is quite intense, but hey, we've learned about nMigen, and that should be enough to allow us to start on our 6800 CPU implementation, which we will get to in part 3, so stay tuned.